Question 8. Nearest neighbor regression. Continuing in the same plague setting as the previous problem, suppose that instead of classifying whether a given citizen will survive, we want to use the nearest neighbors to predict the citizen's probability of survival. We will use the following method. Find the k nearest neighbors of the unclassified citizen according to the methodology in parts G and H of the previous problem. So just finding the k nearest neighbors. For each of the k nearest neighbors, define their weight as follows. Let di be the distance between the neighbor household income and the unclassified citizen's household income. So let dA be the difference between the neighbor's age and the unclassified citizen's age. So we can write it out as di equals difference in income, dA equals difference in age. So calculate the neighbor's weight as 1 over 1 plus the square root of di squared plus dA squared. This formula gives a higher weight to closer neighbors. Among the k nearest neighbors, find the weighted proportion that survived. So for example, if k is 3, and the 3 nearest neighbors have survived values of 0, 0, and 1, with these weights, the proportion that survived is the weight multiplied by survived plus the weight multiplied by survived for every single person, divided by all the weights added up. In order to estimate the survival probability of an unclassified citizen using the scheme above, complete the definition of a function knn_prob that takes the following arguments. Train is a 3-column table where the first column is income, the second is age, and the third is survived. Citizen is an array containing the income and age in that order, so we can say it's like this, make array of income, age, and then k is the value of k. So it returns the weighted proportion that survived among the k nearest neighbors. So fill in the blanks to implement the function above. So let's go back to this weight function really quick. This formula looks pretty daunting at first. It has these square roots and squares and division and stuff. But what it's really important to realize is that this function right here is just the Euclidean difference, or the Euclidean distance, between the two people using their income and their age. So square root di squared plus dA squared equals Euclidean distance. And that's really important because in this function, one of the lines here actually wants us to calculate the distances. Okay, so let's fill out these first 2 lines first. So income diffs, as the name sounds, it wants you to find the difference in income between your citizen and your incomes from the training dataset. So to get an array of all the incomes of people in the training dataset, we do train.column of income, because that's one of the columns it has. We want to subtract out the citizen's income. Okay, so citizen is an array with 2 things, but the important thing is that income is the first thing. So we can say citizen.item of 0. Then the second column is age diffs. So we do a very similar process. So to get the ages of everyone in the training set, we do train.column of age, and we subtract out the citizen's age. And so that would be citizen.item of 1. Because remember that age is the second item in the array. Okay. Now, distances is the Euclidean distances between income diffs and age diffs. So it says np.square root, and let's refer back to our formula here. It's the square root of di squared plus dA squared. So di is the distance of incomes, so we can say income diffs all squared plus, and then the other thing is the difference in ages. So we want to square the age differences too. Age diffs all squared. So this will calculate the Euclidean distances between our citizen and each person in the training dataset. So now we want to do train dist. So it starts out by giving us this table train. And so what it wants us to do is add all these distances to our train table. So the function to add a new column to a table is train.widthColumn. The first argument is the name. So let's just call this distances. And then the second argument is what we feed in. So we're going to call it distances, because that's the name right here. Okay. So NN stands for nearest neighbors. So we want to find the k nearest neighbors here. So let's so now we have all the distances, and remember that the nearest neighbors have the smallest distance. So we want to get the k rows of the table with the smallest distance. So how can we do that? We can sort the table. So we can sort by distances, and then we can set descending to true or false. We want it to be false because we want the first things in the table to be the smallest distances. So we want to sort from smallest to largest. So descending equals false. And then we want to take the k first rows, and the function we can use to grab rows out of a table is take, and we want to take the first k rows, and we can do that by doing np.arrange of k. So that's nearest neighbors. Our weights is going to be, we can take the distances out of the train table, because remember we need distances to calculate the weights, because the weight is 1 over 1 plus the distance. So we can say 1 over 1 plus weights, or not weights, sorry, train.column of distances. So this will give us an array of all the weights. So weighted sum is what we want to calculate here. So we basically want to figure out, we want to multiply each weight by whether or not they survived. So it gives us two things to multiply together. So the first one should obviously be our weights. And then the second one is whether or not they survived. And how do we get that? We can do that by taking the array survived out of our table, train. So train.column, survived. Okay. So now it wants us to return weighted sum divided by something, and that something is the sum of the weights here. And we can take the sum of the weights by using the np.sum function. So np.sum of weights. And then we are done. We finished our classifier using the weights.